Thank you very much. I shall lecture in English. I'm sorry. Actually, it's better for you this way, I reckon. It's a great pleasure to be here. I'm very happy to be in Kyoto for a long time, for 8 weeks. So I look forward to my time here. I look forward to talking with you. And today I want to give an introduction and to my lectures. And I want to explain some words to make sure we all understand some things. So we'll begin at the beginning. These lectures are about what are called reductive groups, real reductive groups, and their representations, especially what are called tempered representations. And I want to study these representations using C-star algebras. So the other thing I want to discuss is using C-star algebra. Okay, so I will discuss all of these things today, but I'm also going to give you the end. When you read a book, it's always good to look ahead to the last part of the book to see if anything interesting happens in the book. And so I want to explain to you what the final conclusion will be. Today I will describe these things, define these things, and describe our objective for the 8 lectures. After the 8 lectures, we can look back and we will see that this is what we have found. So let me give you this picture so that we know what we're heading towards. So when I say the end, I mean not the end of today, I mean the end of all 8 lectures. So that will take us almost to June. And I'll illustrate where we'll end up with this example. This is an example of one of these groups, one of these reductive groups, real reductive groups. So we're trying to understand the representations of this group, the representation theory of this group, what are called tempered representations, which are the ones that Harishchandra studied in detail. And the final conclusion is going to be this statement. Tempered representations, whatever they are, will be mostly determined. The theory will acquire its shape from the following geometry. So now I'm going to draw pictures, and the pictures are supposed to tell everything, and see if I can draw these reasonably well. What I'm drawing here is a cone, a right circular cone in R3, and inside of this cone I want to draw a hyperboloid like this. This is my favorite picture. Like that. And I'm going to draw 2 pictures. Well, I'm going to describe a second picture. It's a little hard to draw it because it's in R4, not in R3. What I've drawn here, let's call this group G, as I did. In fact, is our homogeneous space. It's a picture of SL2R divided by SO2. And what I've drawn here is a picture of SL2R divided by some other subgroup, and I'll call it MN. People do. I'll tell you what it is. It's just a set of matrices which look like this. So SL2R means 2 by 2 real matrices with determinant 1, as you know. And I've drawn 2 homogeneous spaces here, and they sit naturally in this particular case. These sit naturally in R3. And one way of doing that is to think of R3 as the Lie algebra of our group G. So it's a set of all matrices, 2 by 2 matrices with trace 0. And SL2R acts on this set of matrices just by conjugation. And now you can find that a single orbit under that conjugation action can look like this, or it can look like this. There are other orbits as well, which are less important. And I'll come back to this picture in just a while. Just a while. Let me draw. Here's picture number 1. Here's picture number 2. So picture number 2 is I have to describe in words, not in terms of an illustration like this. I want to build a big space. And this big space will just be the set of all matrices, it's called T, which are 2 by 2 real matrices. And there's only one condition, which is the matrix is not 0. So it's all the non-zero matrices, not invertible, not 0 matrices. If I have a matrix, I can take its determinant. The determinant will be a real number, like this. And this is a decent map. This is actually a submotion of manifolds. Of course, X is 4-dimensional, makes it a little difficult to draw. But it's rather interesting to think about what fibers of this map are, the point inverse images of this map. The fiber over a typical point T. Typical means anything except 0. So it's a set of all matrices with determinant some number T. Okay? If you have any 2 matrices with determinant T, as long as T is not 0, they differ by multiplication by a matrix of determinant 1. So this is, each fiber is a single copy of SL2R. Fiber over T is equal to 0. So these are the non-zero matrices which have determinant 0. So they're non-zero, but they're not invertible. In other words, they have rank exactly 1. It's the set of all rank exactly 1 matrices. And of course, one can work out what it is in terms of group theory. But all I want to describe right now is that it's a cone, like this space here, because if I have a matrix of determinant 0, and I multiply it by a scalar, 2, 3, 4, whatever, then of course it still has determinant 0. So this space of matrices of determinant 0 is a cone, like in this picture. So this is a more elaborate version of this picture here. Indeed, we could augment this picture if we wanted to, put in other copies of SL2R divided by SO2, which increasingly approximate the cone. So the group G, this particular group of 2 by 2 matrices, is a deformation of a very much simpler space, which is just a cone, which has additional symmetries coming from rescaling. And we want to study representation theory, a subject which seems far away from geometry, especially this sort of elementary geometry. But the message of the lectures, the conclusion of the lectures will be that this easy geometric picture, and this one too, will tell us nearly everything about the representation theory of one of these groups. Nearly everything that Harishchandra did can be summarized in a beautiful way in terms of these pictures. This is what I want to describe to you. So the emphasis will be geometric, even though I will have to talk about C-star algebras, representations, analysis. Somehow the emphasis will be on very simple geometry. So geometry, analysis, representation theory, and a little bit of algebra. So this is where we eventually will head, and but this is where we will start. Let me have a little discussion with you all. Please ask questions if you are upset about something. If you do not understand something, please ask a question. I really like it when people ask questions, so please ask questions, especially the students. In fact, I think it's more likely that you will ask a question.
Okay, I'll
Good.
I'll control myself.
Good. All right. So far, so good? Yes, it's good. Any problems? No? I want to, there are not so many of you, so it's very important that I do not lose anyone each day. Each Friday, I need you all to come back, because there are not so many. All right, so let me begin. So I hope this seems a little bit interesting, a little bit attractive, but let me begin over here with some boring definitions. Not so interesting. And then hopefully we'll get more interesting in a little while. Eventually, I want to consider specific groups which have some interesting geometry like these ones here. But to begin with, suppose use just any topological group. I want to study unitary representations of G. These tempered representations are examples of unitary representations. It's just a homomorphism of groups, as you know. From G into the group of unitary operators on a Hilbert space. And there's a mild continuity condition which says that whenever you pick a single vector or two vectors, doesn't really matter, let's just take one. I can build a map from G into the group, the action map, in this way. Oops. Sorry, I was made a mistake there. Managed to correct it. Say it this way. So H carries its norm topology, it's a metric space, and G is a topological group. there are different ways of attempting to define continuity, and this is the only good one. There are variations on this definition, different definitions that you might try to study, but they're no good. This is the only good definition of continuity. Anyway, we can speak of equivalence of representations. Of this type. We can speak of direct sums of these representations. And we can speak of irreducibility of such representations. And unless you ask me to, I will not define these precisely, because I think these concepts are very natural, probably familiar to everyone. Okay, the most important maybe is irreducibility. It just means that there's no closed subspace of H which is mapped into itself by every group element. And then you can build this space here, G hat, so-called unitary dual. And it's just all irreducible representations of equivalence, all irreducible unitary representations. Let me just make one small point here. Zero Hilbert space is a legitimate Hilbert space, but it doesn't make a legitimate representation. Any trouble with that? Any questions? Everyone happy? Happy? You can't say much more with this degree of generality, so let's immediately reduce the number of groups a little bit. Let's assume that G is, well, nothing crazy, some Hausdorff group, of course. I won't mention these things again. And nothing crazy, second countable. And the key thing I want to write down here is local. Then the basic theorem for these groups is that there exists what's called a Howell measure, as you know. It's a measure on the Borel sets inside of G. It's finite on the compact sets, and it's translation invariant. So for every measurable set E, it's basically unique. You can multiply it by 2, and then you get a new Howell measure, but that's all you can do, multiply it by a scale. Now suppose I look at the set of all continuous compass values. Finally, it's compactly split functions on G. Then on this space, we can define a couple of things. Where should we do it? Let's do it up here. On this space, we can define 2 new structures. one makes it into an algebra and the other makes it into a, well, in a product space. Of course, there's a standard in a product, which is just the integral over g of f1 of g 2t. The other thing you can, and this was just a scalar, it's an inner product. The second thing you can do is define a convolution in this way. Just too many g's. I'll write this how measure R integral is just dh. And if we complete the smooth or the continuous compact exponential functions in this inner product, or the norm associated to this inner product, of course we get L2 of G, Hilbert space. On the other hand, if we treat exactly the same space in a different way, by making this convolution the most important thing, then what we'll end up with is what's called a reduced C-star algebra of G, and let me say a few more words about that. The first thing to say about it is that it's an algebra, and the second thing to say is that it's an algebra of operators on this Hilbert space, bounded operators on the Hilbert space. And so just to be sure, I'm going to give you the definition, make sure you know it. I was in India in December. I went to India and I gave some lectures in India. Just 5 lectures, 5 hours, not 16 hours, only 5 hours. And so I gave 5 lectures, and the people, they said they liked the lectures, and but then one member of the audience said at the very end, those were really wonderful lectures on the C-star algebra of a reductive group, but if only I knew what the C-star algebra of a reductive group is, then I think I really would have learned something. So now I'm going to tell you, just to be 100% sure that you know what this thing is. So here's what we do. I have a function, then I can make an operator out of it in the following way. Lambda stands for left. And just left application of f as a convolution, as up there, left convolution. It extends to a bounded operator, continuously to a bounded operator on this completion. And the C-star algebra, the thing I want to study in these lectures, is just the closure in the operator norm topology inside of here, of the set of all of these. So now you officially know what this thing is. And it's an algebra. We start off with one vector space of functions on G, and you can either build, depending on your preferences, a Hilbert space, L2 of G, and this is what Harris-Chandra did, and this is what he studied, or you can build a C-star algebra, which is not what Harris-Chandra did. But he might have, because it's a very similar object. It's just the completion of the space of functions in a different norm. So it's a different functional analytic way of treating the compactly supported continuous functions. And in one way of treating this space, you get a Hilbert space, and in the other way, you get an algebra. Okay, so we'll study both at the same time, but mostly we'll study the C-star algebra. Oh, maybe I So let's, for simplicity, assume that G is a unimodular group. It means that the left invariant Howell measure, which was up here somewhere, is also a right invariant Howell measure. Here we go. Instead of multiplying on the left, let's imagine that multiplication on the right also didn't change the measures of sets. If that's the case, you say that G is unimodular. In that case, given any function f, you can build a new function f star in the following way. And this defines an involution on this space of functions with this convolution multiplication compatible with operator adjuncts of operators. In other words, the adjoint of the operator lambda of f is the operator lambda of f star. Okay. And we obtain what's called a C-star algebra in this way. And so we want to study this. And we want to apply some geometric ideas to these objects coming from functional analysis. All right. Let's do an example to try and understand a little bit of what's going on. Keep this picture for a while. Let's keep this. Let me do the world's easiest example so you get a feeling for what this thing is that we built. In this example, I want to consider the abelian group, which is just the additive group of real numbers. But it's a little more satisfactory not to call this group R. Let's just take here any real finite dimensional vector space. If I have a function on the vector space, and of course it has a Fourier transform, which is a function on the dual vector space instead of linear functional, and it's defined in this way, as you know. So let's equip V. Let's pick a measure on V, a Howell measure on V, in other words, a copy of Lebesgue measure, and then form this. When I do that, I get a function, just to make sure we understand what's going on the dual vector space. This has been studied quite a lot, as you know. And let's see, what do we know about this? There's the famous Poincaré formula, which is a formula which tells you how to reconstruct a function, for example, the value 0, out of its Fourier transform. If you think about it, once you've chosen a measure on V, there's a natural corresponding choice of measure on V star, and it's a fact that you can reconstruct the values of the original function and the values of the Fourier transform in this way. There's some constant, it's not that important for us. There it is. Now, if I have a function f, which is actually the convolution of another function h with its adjoint, like that. And if I calculate what is f of 0 according to the laws of the involution and the convolution up there, then it's very easy to do. What you find is that this is always just the L.1 of h. Secondly, if you calculate the Fourier transform at any point of phi, what you find, it's easy to do the calculation, is that this is just the absolute value of h hat of phi. If you put these things together, you get a formula out of this. Which says that, well, there's some constant, c here. So the Fourier transform is a unitary isomorphism after you adjust by a constant from L2 of v to L2 of v star. Picture. This is to keep us inspired. Do some geometry at some point, not today. So in a mysterious way, these are one and the same Hilbert space. If these Hilbert spaces are the same, then the algebras of operators on them are also the same, can be identified with one another. Now you can calculate, it's not very difficult once you know the basic theory of Fourier transform, but this map here sends the C-star algebra of V. So V is our commutative group. The C-star algebra of V, where is it? Sits inside the bounded operators on L2 of V. Here we go. And so it maps to some other algebra over here. What it maps to is what's called C0 of V. So this is the continuous functions on V, V sub. The continuous complex valued functions on V which vanish infinity. It's the closure in the supremum norm of the compact exploitative functions. And it's an algebra under the easy operation of pointwise multiplication. And it acts on the L2 space in the obvious way. If I have an L2 function and I have a continuous function, I just multiply them together, and it's still an L2 function. The continuous function is bounded. So this C-star algebra just looks like this algebra here. It's a commutative algebra. Of course, it was commutative to begin with. But now we see exactly what's going on. This algebra somehow reflects the structure of V star as a topological space. So we've calculated the C-star algebra of one group using Fourier theory, and our goal is to consider more complicated groups like this one here. And when we do so, it'll be a lot more challenging, and we'll have to use some geometry, as you'll see. In order to give you an idea of what these C-star algebras look like and what they're good for in more complicated cases like this, it's not enough to consider this one example. It's a little bit too easy. In fact, it's not enough to consider two examples, but I do want to consider separately the case of a group which is not abelian like this, but which is easy in another respect, namely it's compact. So I want to tell you a little bit about compact groups. But before I do that, let me just say a few words about C-star algebras. which will be helpful. So first of all, just in case you don't know by now, this is since over the last 50 years, I think this has become a standard topic in mathematics education. But anyway, what this means is the C-star algebra is just a Banach algebra together with an involutional Banach algebra, an operation which sends each element to some other element, and then there are various laws. I'll just write down a couple of them here. I guess the only other law is that the star operation should be conjugate linear. And there's only one other thing. There's only one other thing to write down, which is this wonderful C-star identity. It's a sort of a mysterious thing, but this strange C-star identity allows you to speak, to understand with total clarity what are the C-star algebras which, like this example here, are commutative. If the C-star algebra is commutative, if you have a Banach algebra with this additional structure, and it happens to be commutative, then it's always the functions, the C0 functions on some space. Studying C-star algebras, if they're commutative, is exactly the same thing as studying locally compact topological spaces. Okay, that was not very hard. A representation of a C-star algebra is just a star homomorphism, an algebra homomorphism which preserves the star operation homomorphism. And there's only one other condition, which is that the representation should be non-degenerate. It means that if you look at all products of operators and elements in the Hilbert space, go back to Hilbert space. So for example, the zero map from B, which sends every element of this C-star algebra to 0, that's an algebra homomorphism, but we don't allow that. That's rubbish. Oh, and as before, we don't allow the 0 space. That's also rubbish. And so you can do representation theory for C-star algebras. Notions of equivalence, just like we had for groups. Direct sum, just like we had for groups. Irreducible, just like we had for groups. Nothing very fancy. Each time I have a C-star algebra, I can build a set, which is just the dual or the spectrum. Of the C-star algebra. And it's just the irreducible representations of the object. I defined the reduced C-star algebra, and let me define its friend, the full C-star algebra of G, now, just so we have it. The C-star algebra that I was talking about before had a little r. There was a little subscript. Up there, there's a little subscript. Here, there's no subscript. And so this thing is defined in the following rather abstract way. It's just a completion of our friend, the vector space of continuous compact exploitative functions in a norm. the norm of some element f, C star G norm. It's just the sup over all pi of the norm pi. So this object was invented in an effort to understand representation theory, and that effort was mostly unsuccessful because the definition here is too abstract. But the connection with representation theory of groups is very equal, very simple. The representations of this C star algebra are the same as representations of G. If I have a representation of the group, I can convert it into a representation of G by the following formula. So f is a continuous compactly supported function. It takes a little bit of effort to understand the meaning of this operator integral. So this C star algebra has the pleasing property that its spectrum is just exactly equal to the unitary group of G. That's the good news. The bad news is that neither this nor this is really that accessible. So this object is less useful than it might seem because the norm here is too abstract. How could you possibly calculate this norm without knowing beforehand all of the representations? But if you knew the representations, you wouldn't need the C star algebra to calculate them because you would already have them. So this is not so useful. But anyway, a nice abstract. Among the representations of G, we don't have a big supply of representations of G. If I give you an arbitrary group and I ask you, show me some representations, what do? You can probably show me the trivial representation in which every group element acts as the identity operator, and you can show me the regular representation, as I described. That's about it. But by studying the regular representation, of course, according to this universal property, we get a homomorphism like this, and it's not difficult to show that the image is exactly the C star algebra G. It's a curious fact about C star algebras that the image of any C star algebra homomorphism is always a closed subalgebra of the target. Oh, by the way, I wanted to make a point about star homomorphisms here, which is that they're automatically, just to remind you or tell you, these are automatically continuous homomorphisms. In fact, no bounded homomorphisms between bounding spaces of no less than. That's a fact that C star algebra is. The quotient map, let's just put this. As I just was saying over there, this C star algebra is a quotient of this one by some closed two-sided ideal. And if you think about it, that means that the spectrum of the reduced C star algebra is embedded as a subset spectrum of G. Because if I have any irreducible representation of the reduced C star algebra, I can just compose it with this thing and get an irreducible representation of the C star algebra of G. As I explain, this is just G hat. And the image inside of here, of the representations of this reduced C-star algebra, is what's called the reduced dual. And that's the collection of representations that we actually want to study, at least in the case of the special groups that we're going to look at. So I apologize for these maybe not so interesting things. Oh, let me just do one more example. Let's get back to something else. I have a topological space, a locally compact space X, and I look at the C-star algebra of all continuous functions vanishing into infinity on X, then it's a famous theorem that you can reconstruct X by taking the spectrum of B. The only possible ways of getting irreducible representations of this C-star algebra are to pick a point in X and look at evaluation at that point, which gives a homomorphism to the complex numbers, which is the algebra of all bounded operators on the complex numbers. All right. Oh yeah. So now let's go back to compact groups. So we made a little digression into C-star algebras so that we could have some language, not very complicated language, to discuss what's coming next. So these were studied by Peter and Weil about 100 years ago. Nothing so new. Oh, by the way, I forgot to say that this thing was invented exactly 70 years ago. It has a birthday. So happy birthday to the reduced C-star algebra. We had a conference for L.1, Pugh medalist, who was also turning 70. So the C-star algebra of G shares a birthday with L.1, more or less. So one of the things that Peter and Weil showed is that every irreducible unitary representation of G is in this so-called reduced dual. And while we're at it, every irreducible representation, unitary representation, is finite dimension. And if I have an irreducible finite dimensional representation of G, then since the reduced dual and the full dual are the same, it corresponds to a representation of the reduced C-star algebra. Now, as bounded operators on, I'm just going to write endomorphisms on this finite dimensional Hilbert space. And the theorem proved by Peter and Weil is you can take all of these individual homomorphisms collectively and build the following object. Which is an isomorphism of C-star algebras. And I just need, so the sum here is overall irreducible representations of G, which are equivalents. just need to tell you that this thing is what's called the C0 direct sum. What it means is you look at sequences of elements, one from each of these C-star algebras, each of these operator algebras, and the sequences should have the property that the norms of the elements in the sequence should converge to 0. So they converge to 0, not arbitrary sequences, but sequences which converge to 0 with the elements taken from these constituents. Okay? And when you put all of these things together, this is what the C-star algebra looks like. So it's very, very simple. And what we'll eventually see is the two very simple examples that we've dealt with, compact groups and abelian groups, somehow are reflected through this picture in the theory of more complicated groups. Let's say one more thing. Oh yeah. There's an important point which I forgot to mention back here, so now let me right here, which is that if B is a C-star algebra, then its spectrum is not just a set, it always carries a natural topology. And one of the nice things about C-star algebras is that there's a very simple way of describing this topology. What's called the whole kernel topology. And in this topology, the closed sets of irreducible representations correspond exactly to closed two-sided ideals. And the correspondence goes like this. If I have a closed set here, and just this sitting inside of B hat, I can build an ideal, which is just the intersection of the kernels of all of these pi's. Each pi is, after all, an algebra homomorphism, so its kernel is an ideal in B. I just take the intersection here. So and this builds an ideal, and of course you can go in the other direction. If I have an ideal, I can build a closed set, namely the set of all pi's such that pi on the ideal is 0, which of course f of j, and this thing here, j of f. So here are two operations. One takes close a set and builds an ideal, and the other takes an ideal and builds a set. And the sets that you build in this way are by definition closed sets. You just decree them to be closed sets. And when you do that, you get this space topology. And if you look at this example, and you start off with a locally compact space, maybe, for example, just the real line, and now you reconstruct the space as the space of irreducible representations. You reconstruct the space not just as a set, but as a topological space, so that the C-star algebra remembers and carries exactly the same information as the topological space in this example here. So this fellow here, this line, is also an example of this construction here. If I think of X now as being topological space. And to return, maybe let me reformulate. What we just saw for abelian groups. And for compact groups, if G is a real vector space in a abelian group, then what we saw is that the C-star algebra of B is just the C0 continuous functions vanishing at infinity. So another way of saying this is that the C-star algebra is isomorphic to. These are functions on the reduced field, and the same thing is true for complex. Except that the functions are a little bit more complicated. They're operator value functions. These give us an indication of what to expect abstractly when we build the reduced C-star algebra of any group. We expect to be able to think about the C-star algebra as just continuous functions on the dual, possibly with values in operators, not values in scalars, like in this case here. That's what we expect and hope for. The story can be more complicated in general, but for the groups we will study, it's not more complicated. That's exactly what happens. Okay, so these are somehow very elementary things. I hope you're mostly still awake from going through these things. I felt I should say these basic things about what is a C-star algebra, what is the reduced C-star algebra, because I learned that sometimes people do not know them. But now you know what is the reduced C-star algebra. Yes? You still don't know. Okay. Any questions? Still feeling strong? Feel strong? Ready to continue? Sushi? You feel strong? Then we'll continue. Should bring next time a big bottle of sake. All right. How many people already knew what is a C-star algebra, what is the reduced C-star algebra? How many people already knew these things before the lecture? You'd put up your hand, you knew. How many people took a class in representation theory? How many people knew about representations of groups? Representations of groups? It's okay, please. Okay. How many people are following? Do you understand everything that I said? And finally, how many people are confused? Not confused? All right. Here's something. Let's try and raise the level of the discussion a little bit. Let me return to this happy birthday. So this was invented by and what he was interested in doing was the following thing. He was interested in understanding how to generalize the theorem of Poincaré that we mentioned earlier. And this theorem was if you like, the starting point for Harishchandra's work. As you'll see, this theorem is very abstract. This abstract Poincaré theorem is very similar to the abstract theorem of Peter and Weil that we had over here. So here's the problem. And given a group G, it might be, very soon it was worked out by, in fact even before Siegel's work, it was understood by von Neumann and others, it was understood that what I'm about to tell you cannot work for an arbitrary group. So there are some hypotheses, I'll tell you about them in a moment. So what's the problem? The problem is to find a measure mu. It's not a measure on the group, it's a measure on the dual group. And this object here is going to be called a Plancherel measure because it will appear in a sort of Plancherel type theorem. In fact, I said this theorem is abstract, so in fact, rather than find, the first thing you might want to do is prove that one exists. And what's this measure supposed to do? Here's what it's supposed to do. Supposed to reconstruct functions from their Fourier transforms in the following sense. So people experimented with some formulas like the ones that I showed you back in the abelian case, and they decided that what I'm about to say is the right generalizations. In the classical theory of Plancherel and Fourier and so on, you took a function on G and you wrote down a formula for f of 0. So it's easy to guess that 0 should become E, the identity of the group. Okay, and maybe there'll be some constant. Of course, in the formula, this constant could be absorbed away, as you'll see. Now, what are you supposed to do? Well, the integral is going to be an integral over the unitary dual of G, like we were looking at in these situations, perhaps. Remember, these spaces are basically the same, just some different norm is involved, basically the same as L2 of B and L2 of these stuff. Okay, now what are you supposed to do? Well, after some thinking, it was decided that this is the right thing to do. If I have a function on G, you can think of it, as long as it's a compactly supported function, as an element of the C-star algebra of G, and I can convert any representation of G into a representation of the C-star algebra, and so I can form pi of f, and it's an operator on some Hilbert space. And I can represent that operator as a matrix, big, infinite by infinite matrix, and I can take the sum of the diagonal entries, that's the trace, just like it usually is for matrices. Okay. And then I can add up. How do I add up all of these contributions? Well, that's what this measure does. And as I was describing back in the classical Plancherel theory, you can write this in some different ways. Maybe the way I'm about to write it it's a little safer, it's a little more mathematically secure. So first of all, let's say that's so at least get started. As I explained, there are two ways of writing down Plancherel's formula, and one looks like the formula above, and another one involves norms, somehow a little bit better, and they're equivalent. Some spaces. the only thing that's a little bit tricky is to figure out what the correct way of taking this norm is. This should be what's called the Hilbert-Schmidt norm. If I have an operator on a Hilbert space, I can choose an orthonormal basis for the Hilbert space, and then the operator can be represented as a matrix, like you see in linear algebra. Matrices operators are basically the same thing. And once I have a matrix, I can attach a size, a norm to that matrix, just by squaring each entry of the matrix and then adding them all up. I define that to be the norm squared of the matrix, the so-called Hilbert-Schmidt norm. And that's the norm that I'm using here. It's not the operator norm, it's some other norm. But here's the beautiful formula. And so what Siegel proved is that indeed a measure mu exists, and for that matter is unique. Subject to some hypotheses which I'll tell you about now. The first hypothesis is it's a very good exercise to see that this hypothesis is necessary. Good exercise to see that this is there's no hope for this formula unless G is unimodular. But that's okay, because for the groups who are interested in G is unimodular. As for the second hypothesis, I need to tell you a little bit more about C-star algebras. A little bit more C-star algebras, just a very little bit. And the reason you might need more is that in this expression, there would be a big problem in this expression if when you added up the squares of the matrix entries of pi of f, you always got infinity. Remember, the Hilbert spaces typically will be infinite dimensional. The Hilbert space is a reducible representation. There's no guarantee that this number is finite. And if this number is infinite too often, for example, if it's always infinite, as can happen, then or this can almost always happen, then you're in big problems. There are examples of groups for which the only irreducible finite dimensional representation is the trivial representation. That's quite common. And for those groups, it's not obvious that this will ever be a finite quantity. So there are some technicalities. And they're avoided by making a little bit more assumptions. And these assumptions involve the notion of compact operators. And let me say just a couple of words about that. Then I'll return to Siegel's theorem. And soon we'll be able to get back to SL2. So suppose I have a Hilbert space. I'm imagining infinite dimensions, otherwise it's not so interesting. If I have a couple of vectors in the Hilbert space, then I can build an operator. Let me call it, how shall I do it? I want to build an operator out of these two vectors, so it will be an operator H to itself, and here's how I'll build it. If I have a vector X I'll take the inner product of W with X, like that. Space here. Now it's convenient to imagine that the law of scalar multiplication in vector spaces is a right multiplication, not a left multiplication. It doesn't matter, but this, of course, is a scalar, and I just want to multiply it by the vector B. So this is a scalar multiple of the vector V. So X is sent to a scalar multiple of the vector V. I put a little star here because the way the convention I'm using is that inner products are conjugate linear in this variable and linear in the second variable. So this is conjugate linear in W plus linear in V. This is an operator whose range is one-dimensional, as long as V and W are not zero. So most one-dimensional. It's a finite rank operator. In fact, every operator whose range is at most one-dimensional is obtained in exactly this way. So the compact operators, C-star algebra of all compact operators, is the closure in the norm topology of the linear span of all of these stars. These guys form a simple algebra. I'm telling you these things because we'll generalize this in a little while. This is a rank 1 operator on a Hilbert space. In particular, it's a bounded operator on a Hilbert space. And so it has an adjoint, and it won't surprise you at all to learn that the adjoint is just this. If I have two such operators, I can compose them. And it won't surprise you at all to learn that the composition is this. So this whole thing is a vector. So there's a very simple algebra that these fellows satisfy. They already, thanks to this composition law and this adjoint law, they already form the linear span before you close it is an algebra, and it's closed under the adjoint operation. And when we close it, you get a C-star algebra. And this thing has a name. It's some fancy K thing. It's a very easy C-star algebra. You can ask, because we're in this way of thinking, what are the irreducible representations? What is the spectrum of this C-star algebra? What are the irreducible representations of this C-star algebra? Well, there's just one. The C-star algebra is by definition represented on the Hilbert space H. That's where it lives. And that is an irreducible representation, and it's the only one to equivalence. This is an example of a C-star algebra whose spectrum consists of a single point. In fact, as long as you stay away from crazy C-star algebras made using logic, so as long as you stick to separable C-star algebras, for example, these are the only C-star algebras which have the property that their spectrum consists of a single point. These are the elementary C-star algebras whose spectrum, whose representation theory is a single point. And while we're at it, let's consider a sort of converse, not converse, but an inverse, transpose, adjoint or something of this. Let's consider representations of a C-star algebra in compact operators. So in other words, I'm imagining I have a C-star algebra B. It's represented as bounded operators on some Hilbert space. But let me assume that the image of the representation consists entirely of compact operators, like this. It's a very easy fact to say that each such representation is just a direct sum of reducible representations, each of which has image some subspace Hj. Complex Hj. I feel I should say this in a better way. Let me say it again over here. Use this little space. So if I have a representation whose image consists only of compact operators, then it's possible to decompose the Hilbert space as an orthogonal direct sum of subspaces in such a way that pi of b is precisely the C0 direct sum of the compact operators on these subspaces, and each individual subspace is an irreducible subrepresentation. It's not the case that each representation of a C-star algebra decomposes into a direct sum of irreducible representations. This is not the case at all. If you look at the action of the group R, or the C-star algebra of R, on L2 of R, this is a perfect example of what goes wrong. If a representation is not irreducible, you can divide it into two sub-representations. And if each of those is not irreducible, you can divide them again, and again, and again, and again. But there's no guarantee that this process will stop with a decomposition into irreducible representations. There's no guarantee because the representations are not finite dimensional. But these compact operators give you a guarantee that the process of taking a non-irreducible representation and dividing it into smaller representations, this process eventually will stop. There's a guarantee, and it comes from this idea of compact operators. So these are the best representations. They have an elementary character to them, which is reminiscent of the representation theory, for example, of groups on finite dimensional spaces. And hypothesis number 2, go back. This is stronger than you actually need, but this is the easiest one to describe. Is that pi is irreducible. Then I of the C-star algebra of G is contained, in fact, necessarily has to be equal to in case of irreducible. In English, this is called the CCR property, which means completely continuous representations. Completely continuous is another word for compact. So Siegel argued successfully that if a group is unimodular, and if it has this CCR property, then there exists a unique Plancherel measure. The existence comes from some abstract theory, like the Riesz representation theorem. It doesn't tell you what it is, but it tells you that the measure exists. And so you have such a beautiful formula as this. And now I want to show you how this looks for SL2R. very interesting. So what I'm going to describe here is highly non-trivial. To give all of the results just for SL2R that I'm about to write down is not much easier than to listen to all of the lectures I'm going to give. So it's, even for SL2R, what I'm about to say is highly non-trivial. So this group is unimodular. And it's possible to argue, one of the things we'll do in this lecture is, in this course, is we'll show this. This has the CCR property. It seems amazing that you could prove this CCR property because it sounds so abstract. How could you ever prove this for a particular group? In fact, it's not so difficult to check this condition in many cases, including this case here. It looks very abstract. How could you ever do it? In fact, it's not so bad. Anyway, let's just agree that this property holds. And then, on the basis of this, we can discuss the Planck-Charel formula up there, and also the structure of the C-star algebra. Those two problems are very, very similar. So a long time ago, almost at exactly the same time that C-star algebras were invented, so 80 years ago, not 70, but 80 years ago. So this was computed by Bargmann, a mathematical physicist. So these are irreducible representations of G. They all turn out to be in this reduced dual. Oh, I forgot to mention something. I'll come back to it later. First of all, there's an extremely interesting family of representations which is called the discrete series, and one of the reasons it's called that is that the representations are labeled, parameterized by integers, by the discrete set. I'll write them as representations of the reduced C-star algebra. I'll call these open spaces Hn, where they live. I shall not describe right now how to construct these representations. And there's one for every integer except 0. 1, 2, 3, minus 5, minus 6, minus 7, everything except 0. So in the 1940s, Bargmann worked everything out that I'm about to tell you. And then it took about 30 years to understand the general context of what Bargmann discovered, and that's what I'll describe in these lectures. First of all, there's a so-called even continuous series. They're called continuous because they're labeled by a continuous parameter. I'll put even for even, and then there's a continuous parameter S. They're all represented, or representable, and they vary in a continuous way on a single Hilbert space, which I'll call H even, like that. And S here is any, let's say, real parameter. And finally, there's an odd continuous series. And it's also labeled by a real parameter like this. In a natural way, you can identify all of the Hilbert space, and I'll call it H. There's a small footnote about the odd series, which is that when you get to s equals 0, the representation actually isn't irreducible. It's a direct sum of two irreducible representations. We know it's a direct sum of representations by what I just said. In fact, it's irreducible representations. It's a direct sum of two irreducible representations. And here's what happens. It's extremely interesting. Some suspense. I want to focus on one of these continuous series, maybe the even series. Here's the compact operators on the Hilbert space. Each time I pick a number s, according to what I described over here, I get a star homomorphism of C-star algebras from this fellow to this fellow. Now, as s varies, I can put all of those star homomorphisms together, see, to obtain not a single compact operator, but a one-parameter family of compact operators. In other words, the totality of this family of representations defines a homomorphism from this C-star algebra into the algebra of continuous functions from R into the compact operators. And the way it works is that the value of such a function at a particular point S is just pi sub S of the corresponding element in the C-star algebra. Okay, so these representations have a continuity property built into them, which justifies the name continuous series. And the continuity property is that as you vary the parameter S here, the operator over here associated to any fixed element of the C-star algebra varies in a continuous way. And so this entire family is packaged like this. And in fact, you can do one small thing which is a little bit better than this. Let me just tidy up how it looks here. Which is, you can absolutely guarantee that these functions converge to 0 at plus or minus infinity. In classical Fourier theory, there's something called the Riemann-Lebesgue lemma. Which says that the Fourier transform of any, say, continuous and compact exponential function is a function on the line which vanishes at infinity. And it's the same phenomenon here which is responsible for this 0. So these are the continuous functions from R into this C-star algebra whose pointwise norm converges to 0 at infinity. And of course there's something similar for the odd series. And there's a similar sort of Riemann-Lebesgue lemma, which is reminiscent of the Riemann-Lebesgue lemma for discrete Fourier series rather than the Fourier transform. Namely, you can package together all of the discrete series into a single C-star algebra homomorphism like this. And now you can package all of these bits together. In a natural way. Here are the even fellows. Here are the odd fellows. when you package them together, you actually get an isomorphism of C-star algebras. So you've totally described what's going on, except for one detail which I left out, which is that it happens to be the case that the representation built by Bachmann in either the even or odd series of any S is equivalent to the representation built by Bachmann at minus S. So there's a symmetry in these representations. They're not all distinct from one another. The representation of S is equivalent to the representation of minus S. And it means that you don't quite get all functions here. You get functions in both cases which satisfy some symmetry with respect to Z naught. And then that's it. Then it's over. And that's what the C-star algebra looks like. So the C-star algebra of G looks like functions from a certain space, which is R divided by 2, so to speak, union R divided by 2, union a discrete series of points into compact operators. So it's operator-valued functions on a certain space, and that space is the reduced dual. And to go back to, where is he? Up there, the Plancherel formula. More than one person did this calculation, but I'll give the credit to Harris Chandra because he did the general case. Just to show you what Harris Chandra was aiming for and what the answer tends to look like, let me tell you exactly what's going on with this Plancherel measure here. This is the type of specificity that Harris Chandra was aiming for. He wanted not an abstract Plancherel formula, but the following concrete one, like this. There's a constant, which is, I don't think I wrote it down, but I just call it constant. Oh, but maybe I should use this version up here since it's on the board. Harris Chandra made the following explicit calculation. First, there's a contribution from the even principal series. I wrote down some of this. I did write down the constant. As you'll see, it's a little complicated. It's worth me cheating for a moment. Here we go. Oh, I did write down the constant. Actually, I only wrote that in to impress you because the constant has no actual meaning until I specify a choice of Haar measure. But I'll put it in anyway to make it makes me look more clever to say that I studied the constant. Anyway, here's what goes on. It's kind of amazing. Now, once you fix a constant here, the constants on the other side are yeah. How do I call the variable S? This is S times the hyperbolic tangent of pi times S over 2 times the norm of the representation, pi even S of a function squared, because it's the Stoker-Schmidt. So this is exactly an integral like the one you see up there, and the measure is this particular function of strange mixed type, exponential and polynomial type, ds. And there's another formula, similar formula, for the odd continuous series. So the measure mu is this function, this density function, times the Beck measure on the line. And then we need a contribution for each of these discrete series representations. And the contribution is, each of the nth one is 20 by 9. these are the types of results that we're trying to understand. The question that we want to answer is, why are these formulas the way they are? What's responsible for the fact that when you study the representation theory of SL2, there's a part which is discrete in character, like you see for compact groups, and there's a part which is continuous in character, like you see for vector spaces. What's responsible for that dichotomy in the representation theory, some discrete and some continuous? Okay, you see it here, and of course you see it in the C-star algebra. I want to try to give you a feeling for why this is so. Higher-Chandra really cared about these formulas. To be honest, I don't care about these formulas as formulas, but there they are. But you know, one would like to know, what is the general conceptual reason for these formulas? Why do they look the way they do? Roughly speaking, why do they look the way they do? That's the sort of question that I'll hope we can answer. And to go back to these pictures, now let me, I might as well use some glorious color here. If you look at the group G, there's a part of G which is not well approximated by this cone that I mentioned at the beginning. And then there's a part of G not completely well defined, it's defined only in some asymptotic sense. There's a part of G going off to infinity which is very, very well approximated by a much simpler homogeneous space. Oh, and one more thing. As I mentioned, this cone has a symmetry. There's some scalar multiplication here. There's a vector 1 parameter group. Rescaling or translation action along the code, translating in some logarithmic sense. And what I want to explain to you, well, is how to build these pictures. First of all, let's just say that we've already built it as we did for SL2. Oh, I left my colors behind. I want to convince you that the reason that there are discrete series is that there's a part of G which is away from this cone, in the sense that we'll have to make it much more precise as time goes on. And it's this part of G which determines the discrete series, and of course the asymptotic part determines the continuous series. And we'll see that the continuous parameter that exists over here is almost exactly the same as the continuous parameter which allows you to scale and multiply this cone to copies of the cone. Not exactly, that this one parameter group is isomorphic as a group to the group of real numbers, and the s's that you see here are in the dual group in R star, not in R itself. Okay, but this one parameter action is responsible for the one parameter character of these parts of the story here, and then the rest of the story is given by the red part. I want to try and convince you that you can understand not every detail, not this particular function, for example, as far as I'm aware, not every detail, but much of the structure of these C-star algebra or Plancherel formula from this extremely simple picture. That's what I want to tell you about, not today, obviously, but over the course of the lecture. So by the end of the lectures, you will know, you will be an expert in the theory of Harish-Chandra, to the extent that you will easily be able to explain it to somebody else. As for the precise details, you know, that's another story. At some point, one has to do explicit calculations to determine these functions, and that's another story. Those explicit calculations involve the explicit calculation of certain integrals of gamma function type. Okay, we shall not do that. Let me close by just doing what I promised to do at the beginning, namely tell you what is a reductive group and tell you what is a tempered representation. Let me officially write down the definitions of those two things, and then we'll be done for today. We can officially explain our goal for the lectures once we've done that. Let's see if I'm on track here. A little bit behind. So first of all, let me describe what I mean by a real reductive group. Which I promised at the beginning, some promise definitions. So a real reductive group will be for us, a Lie group, almost connected, finitely many connected components. Which can be embeddable, closed subgroup, actually closed is automatic. What else I'm about to say. Inside some matrix group, some G, L, M, R. Not done yet. There's one key condition. The key condition is that these subgroups of matrices are what's called symmetric. If G is in the group, then so is the transpose. This is the matrix transpose operation. Okay, so it's easy to build examples. It's not that easy. These groups don't come in continuous families. There's just a discrete collection of them. In fact, you can classify all of them, at least their connected components. For what sorts of things are we interested in? Well, certainly GLNR itself, or SLNR, these are standard examples. And most of the other examples that immediately come to mind are the symmetry groups of various bilinear forms. So, for example, the symplectic groups on even-dimensional real vector spaces, the symmetry groups of symplectic forms, the symmetry groups of symmetric forms, which have differing signatures, so there's a whole family of groups SOPQ, or the symmetry groups of Hermitian forms. Also, again, add here, of course, all of these groups have complex versions. Actually, when you make the complex version of this, you just get GLNC, the same as the complex version of this. Otherwise, they don't. And there are a few exotic groups that you can throw in that I don't know anything about. This is not exactly Harishchandra's definition. Maybe it's worth stating that if you take Harishchandra's definition, which is in some respects more general than this, but also in some other respects more specific, if you intersect it with this definition, what you get are exactly the connected groups as above. First, we'll see it's important to consider disconnected groups. On the other hand, it's difficult to consider all disconnected groups, and so you have to decide how you're going to treat groups which are not connected. How many of them are you going to allow? And so Harris-Chandra allowed fewer than I did. But this is basically the definition used by Harris-Chandra, almost done. So for every G up here, all the ones on this list, these all belong to both classes. What Harris-Chandra did was he wrote down the counterpart of this formula in as detailed and terrible a form as you see it here. It's like this, only worse, with more complicated functions and more discrete series and so on. In fact, there are different types of continuous series, not just even and odd, but different series of different dimensions. It's very complicated. That's what Harris-Chandra did, and it took him something like 2,000 pages of effort. It's not an easy problem. Okay, so for these particular groups, one speaks of the tethered dual, and there are different ways of saying what this is. One way is to say that this is the support of Siegel's Plancherel measure. So the support of a measure is the complement of the largest open set which has measure 0. So this is a closed subset of the unitary dual. For the groups that we're considering here, this is exactly the set of irreducible representations of the reduced C-star algebra. In other words, the spectrum of the reduced C-star algebra. So it's exactly what we've been talking about. This is a theorem, and not a difficult theorem, but this is a theorem that Harris-Chandra's definition, he defined this. Tempered is a word that comes from distribution theory. It means distributions which are somehow not too big at infinity. And it turns out to be equivalent to what's written here. This is a difficult theorem. This is almost a tautology. And, oh, I already told you. I already told you what is the reduced C-star algebra. So no need to say that again. So once again, our eventual goal determine at least the general form of. Some of the details are too complicated for us. The general form of. Reduced C-star algebra of G, or it's more or less equivalent, Harris-Chandra's Plancherel formula. Which, again, is more or less equivalent to understanding this space for reductive groups. And determine the general form of is, that means find some geometric explanation which tells us why it is the way that it is. Okay, now it's time for me to give you your homework. No? I think even though we have a few minutes left, I think I'll stop at this point rather than start a new topic. So thank you very much. Here is the end of the lecture.
Any questions?
I can ask you questions. Can I ask a question? If it's okay. In sometime soon, not in the next lecture, but sometime soon, we will need to know a little bit more about compact groups. For example, the representation theory of SU2, of SU3. It's very famous that the representations of these groups were completely determined by, in different ways, by Hermann Weyl and by Cartan, through the theory of the Weyl character formula, or the theory of the highest weight. And so my question is, did you see before? Do you know the Val character formula? Do you know about highest weights? So hands up, all of those who know representations of compact groups, compact Lie groups. One, two, okay. Come. Oh, not everything. No. Okay, let me rephrase that. How many people know the representations of the group SU2? SU2. SU3. So we have to discuss it. All right, so that will not be not next week. At some point, quite soon, we'll discuss. We need to discuss compact groups. Harris-Chandra wanted a very explicit formula, and I should say that I forgot to mention it, but every compact group, every compact Lie group is an example of a reductive group in this sense. So what Harris-Chandra wanted to know about compact groups is equivalent to what Hermann Weyl proved about compact groups. The case of compact groups in Harris-Chandra's theory was proved first by Hermann Weyl 100 years ago. And so, of course, we need to learn about compact groups, and we need to understand how compact groups somehow will tell us. And this, after all, is a compact part of the group G. G is not compact, but this is a compact part of it. And we'll see in a strange way that this compact part of G behaves like a compact group. That's part of the theory that Harris-Chandra worked out. All right, so good. Thank you for participating in my sermon.